Welcome back, physicists. In the last couple of videos, we saw that this thing known as kinetic energy, something you may have been familiar with before, kind of pops out when we look at the net work done by an object or done on an object. We're going to look at the work done by a particular force in this video, the force of weight, that force of gravity pulling things down. And by doing that, we're going to see that another type of energy that you may be familiar with, known as gravitational potential energy, kind of shows itself. All right, so let's see what I mean. We're going to look at a scenario. All right, we're not going to be looking at the net work on an object, on this ball, but we're going to be looking at the work done by the weight force. So we're kind of zooming in, focusing on one particular force, the weight of this. In this case, it's a ball. So I have this ball. It's starting at some position, some h naught. Okay, I have some numbers if it helps, maybe 5 meters. Let's say I let go of the ball and the ball is falling downwards. It travels a distance. It has a displacement downwards because, of course, weight pulls things downwards. And let's look at that work done by weight when it goes from here, this starting height, down to here, this final height. Now, I didn't choose 0 because I'm trying to write a general equation and I don't want things to drop off, okay? But let's see what that means. If I want to find the work done, I know that the work done is equal to the force, and that's the force that is parallel to the displacement or the distance. Those two are often interchangeable, okay? So what does that mean? Well, the work done by gravity, that's equal to the weight of the object. I know I have two W's, one being work, one being weight, okay? Don't confuse those, multiplied by d. Now, is the work and this distance or this displacement, are they parallel or do I have to break them into components? In this scenario, they're parallel. I have the weight force acting down, mg is going down, and the displacement is down. So this work done by the weight, that's going to be m times g. And what's the displacement? What is the change in position? Well, the change in position is the difference between this 5 and this 2. It's going to be h naught minus h. Oh, that's what the work done by gravity is. Or if I rewrite it, the work done by gravity is equal to mg h naught minus mg h. Oh, now if you have a keen eye, you might have thought, well, wait a minute, shouldn't you be doing h minus h naught? And you're not wrong, but remember, I have a force acting down, mg, and I have a displacement down, the distance going down. The work done by gravity in this scenario should be positive. If I did 2 minus 5, I'd get a negative answer over here. And I could solve that by putting in a little negative. And when I put in that little negative, I end up with this again. Okay, so this is ultimately the result you would end up with, no matter how you kind of approached it. But notice what we have. Once again, when I look at the work done, in this case by a particular force, I have something interesting. Something is changing about the object. Something, the mass times g times its height, is going from one value to another value. Oh, that makes this kind of fundamental, something important about this object. This is given a name because every time we look at the work done by this force, it pops up. This is coined, this is given the name as gravitational potential energy. Okay, gravitational potential energy. So the work done by gravity, it's this change in what I'm calling gravitational potential energy, mgh naught minus mgh. But I could at a single moment, just because, again, it's pretty fundamental, kind of like at a single moment I could look at kinetic energy. At a single moment, I could be like, oh, what's this gravitational potential energy right here? And that would be based on the object's mass, g, which I know what that is, 9.8, and the height of the object. Okay, so this new term is popping up. So let's get a little details about this new term, a little bit of detail. Gravitational potential energy. You might see it abbreviated as GPE, and in fact, some students put it as the equation, GPE equals mgh. Maybe a little confusing because, you might confuse this as three things being multiplied, but whatever. But in physics, this potential energy, and I'll describe what I mean by that in a second, is universally or conventionally given the letter U. Uppercase U is a potential energy. And since it's a potential based on the gravitational force, it's often U with a little g. That's how you'll see it on the equation sheet. That's how you'll likely see it if you take future physics classes. Now, why is it called a potential energy? There are several ways to think about it, but, this object, if it has some height, it has potential. Like, imagine I'm down here, right? I'm down here, and I look up, and oh my gosh, this person is holding a ball right above me. Or maybe it's a rock. I'm probably pretty nervous if I'm this person, right? I don't want to be standing right here. Why not? Because I know this ball or this rock can do something. It has an energy. It could start falling. Now, it's not falling yet, but it has the ability to fall. It has the potential to fall. That's why it's called potential energy. Or sometimes you might think of it as like it's stored energy. It's not falling yet, but because of its location and because I know gravity pulls things downwards, this ball has potential to start doing something. So that's where that term potential comes from. There are some other potential energies. We'll learn one more a little bit later, and there are a handful of others as well, but we're just focusing on this one right now. So it's the potential to fall. There's something else. This second bullet point is important, and it's kind of weird. It's really based on m times g times height, remember? And just like we saw at the very beginning of this class, whenever we're measuring heights or positions or displacements, we can choose our starting location. This height technically is relative. What do I mean by that? Well, this person is holding a ball, and of course the ball could fall downward. If I made another ball right here, let's say I had a second ball and it was right here. Sorry, I can't make a great circle, but it'll do. It's right on the cliff. This ball could certainly fall off the cliff and hit me in the head. Could this ball fall and hit the top of the cliff? Could it fall right here? No, that doesn't really make sense. It's already there. Or put another way, this girl isn't afraid of this ball falling on top of her, right? Relative to this location, the height of this ball is 0. It has no potential energy relative to this location. But relative to this location, there is a height. So when you calculate the potential energy of an object at a particular location, you might not have to write it out. You don't necessarily have to make it explicit, but you got to maybe think in your head, where am I measuring that height from? Because it's relative. All right, it could be equal depending on where you're saying. You just want to make sure you know where you're measuring that height from and be consistent in problems, okay? Now, the other thing I want to say, this equation is pretty commonly written like this, m times g times h. Again, maybe you could use GPE if you want. Most people know what you mean. On the AP Physics equation sheet, the AP Physics 1 equation sheet, it looks like this, okay? So there's that UG. They have delta y, and, to be honest, this h is a little more common if we're being honest, but it is delta y also, so you could use either of these. All know exactly what you mean. I think they're trying to make the point of this UG, it's based on the height. It's based on verticality, vertical location. This ball's gravitational potential energy does not change if I move the ball horizontally. Okay, it only moves based on the vertical location. Remember where this came from, work. And work depends on the parallel force and that displacement. The force is down and the displacement is down. So I only care about the part that is vertically downward. So that's why I think they have this delta y. Okay, but either of these equations is okay to use. Last little bit, something a little weird. This gravitational potential energy and the work done by gravity, they're related. It's where I got this new equation. But it turns out they're opposites. What do I mean by that? Have this ball going upwards. It starts at this location and it's moving up. If it's moving up, don't forget the equation for that gravitational potential energy is mgh. If it's gaining height, if it's moving up, it is gaining gravitational potential energy. So on the way up, it is gaining. Okay, if I just plugged in more and more height, maybe I'm measuring relative to that surface, the floor, it's gaining that gravitational potential energy. But what's going on with the work? Remember, the weight, mg, is acting down, and if it's moving upwards, the displacement would be going up. So when the ball is going up, these are in opposite directions. The work done by gravity would be negative. So when the GPE is getting more and more and more, the work done by gravity, this negative value would be getting greater and greater and greater negatively. Oh, or the opposite is true. If I had the ball and it was lowering downwards, well, by this equation, GPE would be getting smaller, but then I would have the mg force and the displacement in the same direction. So when this is getting less and less and less, this one is positive. So these two things have an opposite relation to each other. This can be helpful. You might be given the gravitational potential, and you might be maybe looking for the force done by that weight, or maybe otherwise using this relationship. So they're related, but they are opposites of one another. That is not some non-trivial thing, because you might be asked to use this relationship in certain problems. So they're certainly related. They're almost equivalent, but they are technically opposites. When one is getting more positive, the other is a negative value. When the work is a positive value, that means it's losing gravitational potential energy. So that is a little weird, okay? But that's it. That's gravitational potential energy. Where it comes from, like before, it has to do with the work being done by a force. That's all. Thanks for watching.